Good evening, everyone. I request Professor Abraham, Head of the Department of Mechanical Engineering, Adishangara Deemed to be University, to introduce our chief guest to the gathering. Sir, please.
Good evening to everyone. I am K. Abraham, Professor and Head in Department of Mechanical Engineering at Adishangara Deemed to be University, Kudur, AP. It is my honor to introduce our distinguished resource person for this session, Dr. Saravanan Balusamy. Dr. Saravanan Balusamy is a professor in the Department of Mechanical and Aerospace Engineering at the Indian Institute of Technology, Hyderabad. He obtained his PhD from the INSA, France, and later pursued postdoctoral research at the University of Cambridge, UK, between 2011 and 2014. Since joining IIT Hyderabad in 2014, he has progressed from assistant professor to associate professor and is currently serving as professor. His research primarily focuses on combustion science, with expertise in laser diagnostics, internal combustion engines, and alternative fuels. He leads experimental investigations aimed at advancing the understanding of combustion phenomena and developing cleaner, more efficient energy technologies beyond research. Dr. Balusamy contributes to academic administration as a hostel coordinator at IIT Hyderabad and serves as an associate editor for Thermochemical Engineering, a journal under the Frontiers in Thermal Engineering series. With his vast academic and research expertise, Dr. Balusamy has been actively contributing to the advancement of mechanical and aerospace engineering through teaching, research, and publications in reputed journals. He has guided a number of students, collaborated on cutting-edge projects, and continues to inspire the academic community with his contributions. On behalf of the organizers and all participants, I extend a very warm welcome to you, sir. With these words, I now hand over the session to our esteemed resource person, Dr. Saravanan Balusamy.
Thank you, sir. Thank you so much for your nice introduction. I'll share my screen. So that
Yes, sir.
I hope all of you can see my screen.
Yes, sir. It's visible, sir.
Okay. Thank you for having me. So today my topic of presentation is application of hydrogen enriched combustion in domestic and commercial applications. This is my overall outline of the today's presentation. I'll start with some basic introduction about fossil fuels versus alternatives. What are the hydrogen opportunities and challenges that we are facing currently? And what is the meaning of hydrogen enriched combustion? How that is going to be a stopgap solution before we fully migrate to the hydrogen economy. And I am going to show the research that we have been doing in IIT Hyderabad in the form of laminar flames as well as turbulent flames. And finally, we will finish with summary. So, basic thing I think we all have know. We are all of so much addicted to the fossil fuel usage in our day-to-day life. Most of the applications have to come from there. And this is one reason the data from 70s all the way to 2022. So what you can see is that the fossil fuel usage is slowly coming down, all the way from 90 to slightly above 80. So that shows we still are full of fossil fuel usage, and the renewable energy is slowly picking up. Okay, but it takes time. So we have to worry about the climate change, global warming, and the reason the cloud burst things that we have been seeing all over India, and the world also facing a lot of issues with the climate change. So doing business as usual and going with the fossil fuel usage for the next future is really going to be a very tough game for all of us. So we have to see how quickly we can, move into the renewable energies. In that way, fossil fuels, the major thing what we have to see is that what is the advantage we have been facing so far. Here fossil fuel, I'm meaning coal, oil and gas. The major thing is the energy density is very high, okay? Easy to transport, compact, that is a positive about it. Reliability, it is continuously available. Infrastructure is already matured. We have been using this for more than 200 years. So, a lot of best infrastructure is available in terms of handling and usage. Cost is historically cheaper, but of late it becomes volatile due to the geopolitics. And that's where we are coming. In India, we are paying huge amount of money as well as political things. So we have been subjected to a lot of market swings, and that is not good for India. So we have to slowly move from this coal, oil, gas into renewables in the form of solar, wind, hydro, nuclear, and of late we are working on hydrogen and ammonia kind of stuff. The major problem here is that it will have a variability in it. Okay, solar and wind, there are a lot of variability in it. Nuclear is very capital intensive energy source, whereas hydrogen is highly energy dense, but again production as well as storage and handling is a challenge so far with hydrogen. So a lot of money has been going into it, how to produce green hydrogen and how to make energy self-sufficient from Indian perspective. And also in future, we may become a global exporter of hydrogen energy. So that is what the government is looking into it. We have is India's National Green Hydrogen Mission. So the target is like 5 million tons of green hydrogen production per year by 2030. That is the mission that our government is working on. The current price, if you see, it is around 560 rupees per kilogram. That's expensive one, because production cost is one, then there is a transportation cost involved, there is a storage, there is a safety concerns. So that adds price to this hydrogen economy. One way of producing hydrogen is electrolyzer way. Okay, so government has given a lot of subsidy there, and a lot of projects are in the pipeline to produce hydrogen from simple water, potable water, for example. What is the strategic advantage of this? Hydrogen can be very much useful in our industry area, mainly hard to abate sectors. What are they? Fertilizer, steel, refining, chemicals, shipping, and some transport models where there is a lot of CO2 footprint is there. By replacing partially the fossil fuel with hydrogen, we can reduce our carbon dioxide footprint, and that way we can make our industries much more green. And recently, European Union is looking into the green steel production. Okay, like that, there are many avenues where we can look after the green side, renewable energy sources, and reduce our fossil fuel addiction. So what are the opportunities we have in terms of hydrogen? We have abundant renewable energy resources. You can think about solar and the wind. So the idea is using those renewables, convert that electrical energy to produce hydrogen using electrolyzer or some other methods, and then use that hydrogen to produce the energy later, okay, in a renewable way. Large domestic demand pool is there, like I mentioned, hard to abate sectors. There is a huge export potential, which is also one of our green hydrogen mission target. And it can create a lot of industrial clusters, and job creation would be very high. We have to work on the policy tailwinds and funding opportunities also. But though there are a lot of positives, a lot of opportunities for us from Indian perspective, there are a lot of key challenges also, again, India specific. So the first is that the green hydrogen is not a cheaper solution. It's very expensive. And we have to work on the entire infrastructure on storage and transport. We are in a nascent stage. We just started it. So a lot of money funding requirement is there in that front. Again, land, water, and grid footprint, that is something we have to worry about it. In India, how easy or how difficult it is to get these things done. And a lot of technology and manufacturing gaps are there. For example, hydrogen, if you want to store it, we have to store it in a cryogenic form. That means we are talking about pressures in the order of 600 bars and the temperature is in the cryogenic range. Then there is something called hydrogen embrittlement. That's a very big problem. Basically, the material cannot withstand for longer and the hydrogen start to leak, and that will have a safety hazard for any storage systems. So any confined storage systems with hydrogen is a very, very dangerous one, because hydrogen is such a fuel that it can move from deflagration to detonation just like that. And, it will become like a bomb. So storage is a very, very challenging one. And we have to worry about the manufacturing gaps that we have in India. The final thing is the financing. Who is going to support, who's going to fund this kind of a huge infrastructure development? We need to really working on the regulatory safety framework. So there are a lot of key challenges we do have in terms of production, handling, and utilization. So the topic that I'm going to cover from now onwards is more on utilization. Let's say once we have produced a green hydrogen and we somehow can handle all the way to the industry location. Now how we are going to use this hydrogen available with us and start to work on the hard to abate sectors like the steel or anything, boilers, burners. Currently, what we can do is that we have natural gas, LPG, those kind of gaseous fuels are used in many industrial applications. Can we start to slowly blend hydrogen with them so that we don't need to invest a lot of money initially to change the entire infrastructure, adapt ourselves, learn how to do all the things, because we have to train a lot of manpower to storage, handling, and utilization side. So this hydrogen enriched combustion is work as a stopgap solution. Instead of jumping from fully fossil fuel to fully hydrogen, what we can do is that we can go in a phased manner, start to slowly replace and natural gas, LPG applications, and slowly keep on building the infrastructure for hydrogen, so that our curve would be smooth and easy to do that. Many current systems which that can work with natural gas or LPG, they are very much capable to support up to 30% hydrogen by volume. Okay. In fact, we don't need to do any changes. Any system, boiler or burner or industrial gas turbine kind of stuff, you can put 30% blending without any real modifications. But the game is beyond that. This is one curve where GE shows in their website. You can go and check it out. So the idea here is, suppose we want to reduce 50% of CO2 from a gas turbine by moving away from natural gas to hydrogen blending. We have to blend 75% of hydrogen. And as I mentioned, 30% is okay-ish. Anything you go beyond 30%, then the system won't handle it. We have to rework on the entire design, in the entire way of doing combustion, because there is some safety issues comes into picture when we want to burn hydrogen in these kind of applications. So that is what I'm going to show you, how we are trying to mitigate those problems and how we can go higher percentage of hydrogen in our applications. So just one more slide before we jump into the real applications. Opportunities, we can lower the CO2 emissions because we are replacing fossil fuel, which is mostly hydrocarbon, replacing that by hydrogen, which has a zero carbon. So you can see that net we are reducing CO2 in the burning stage itself. Faster adoption, as I mentioned in the previous slide, we can slowly move into existing gas turbine boilers and industrial furnaces. We can start to blend hydrogen into it with the minimal changes, so that we can get trained on utilization, safety, and all the aspects. And the policy making and the regulatory will catch up. So slowly we can, in 10 or 20 years down the line, we will be fully ready for hydrogen economy. The major important aspect is the NOx reduction potential. Okay, by going lean pre-mixed hydrogen enriched flames, that can very much help NOx emission to cut off. This NOx is such a bad emission. I think most of you know acid rain and the kind of health hazard that NOx poses to us. Okay. So by switching into hydrogen, we can eliminate these NOx emissions. Infrastructure readiness, as I mentioned, we can scale up slowly, and then we will be ready in future. So, and finally, it is to bridge the gap. So we will be fully ready for 100% hydrogen deployment, which is going to be the future, because no way we can keep on going with the fossil fuel because of various climate change effects it has. So we have to fully go into renewable energies. So what are the key challenges when I compare hydrogen with the fossil fuel? That we can look into it by seeing this table. Some key parameters are mentioned for hydrogen with respect to methane, propane, gaseous hydrocarbons, ethanol, methanol, liquid hydrocarbons, and gasoline. I want to bring your attention to few parameters because the table is so big, we don't want to waste too much time here. One is the stoichiometric air fuel ratio, mass-wise. So what this says is, suppose I can take 1 kilogram of hydrogen, I need 34.32 kilogram of air to completely convert hydrogen into products, which is water vapor. Whereas if it is a methane, I just need 17.2 kilogram of air for every kilogram of methane to completely convert that into CO2 and water vapor. Okay. So what you can see is that if I want to have a complete product, this exhaust should have only H2O or CO2. We need more air in terms of hydrogen than methane. So the geometry sizing is important. That is why we cannot simply blend natural gas with the hydrogen without worrying about the geometry. The other important thing is the heating value. For hydrogen, if you take 1 kilogram of hydrogen, if you burn it properly with 100% efficiency, then we can unlock 120 megajoule of energy. Whereas methane, it is just 50. So it is not even 50% of it. It's close to 40% of the energy what hydrogen is having. So hydrogen is highly energy intensive fuel compared to hydrocarbons. And the key catch here is why we were unable to go beyond, let's say 30% of blending of hydrogen into natural gas is because of the combustion speed. Okay. So if you see methane, which is around 0.35, which is 35 centimeters per second, is a flame speed, how flame is propagates from one to another. Whereas the hydrogen is almost 9 times of that speed. So if I design a burner which works perfectly well with the natural gas, and you shift from natural gas to hydrogen, the hydrogen is so reactive, so fast, instead of burning flame outside the system, we start to see the flame gets inside the system. That is called flashback. So it will get into the system and it will destroy the system. Okay. So we will end up with a huge explosion. So there is this particular difference, the high reactivity of hydrogen compared to hydrocarbons, is the key challenge what the combustion community is facing. So if you see, you can see in 2 different ways. One is from emission point of view. If I replace fossil fuel with a little bit of hydrogen, that's called hydrogen enriched combustion, we need to pay attention to both NOx emissions as well as carbon monoxide emissions. CO emissions, why? Because we are still burning fossil fuel. We are not fully shifted to hydrogen. We partially replaced hydrocarbon with hydrogen. So we will still have carbon, so carbon monoxide comes as an emission. The other thing is a combustion point of view, flame stability. So you have something called lead load, flashback, and thermoacoustic stability comes into picture. So first, if we pay attention to this, so what you are having see is the x-axis is the firing temperature and the y-axis is corresponding CO and the NOx emissions. So if you pay attention to CO emissions, the blue color curve, you can see that the CO reaches minimalistic value are above 1800 Kelvin. For the same temperature, if you compare NOx emissions start to pick up. In fact, you can see it's started to grow exponentially. And the gray area is the operating range for most of the modern type, burners, boilers, gas turbines. The point here is we want to reduce both NOx and CO emissions simultaneously. Unfortunately, they won't go together. The moment we reduce CO emissions, NOx emissions will go up. The moment we reduce NOx emissions, the CO emissions will go up. See, for example, operating range, you will have higher NOx emissions, very close to high temperatures, whereas CO emission is the lowest. Whereas in the lean blowout limit, we used to have high amount of CO emissions because the combustion is not complete, whereas NOx emission is very low. So there is a trade-off we need to worry about it. That is a problem. The other thing is, as I mentioned, flame stability. As you can see from this video, you can see three different scenarios: blow off, stable, and flashback. So we can see the slow motion now. In the stable, flame is always above the burner, like a Bunsen burner here. In blow off, flame goes out because too much velocity. In flashback, flame gets inside the tube. That means it is getting into the burner system. Then the burner will get destroyed. Okay. What we need is a stable combustion. What we want to avoid is blow off and flashback. Okay. They are the two extreme conditions for any kind of a burner system here. The other one is called thermoacoustic instability. The moment we go to lean side, because in order to reduce the NOx emissions, we end up with combustion instability. As you can see here, the flame is not uniform stable like the Bunsen burner we see, the other bluish color. Instead, the flame start to violently vary. Okay, its shapes changes, its heat release rate changes. This is called thermoacoustic instabilities. And this mostly happens in a confined system. If it happens in a real gas turbine, then the gas turbine is going to be in big trouble. Sometimes we may have to lose the entire gas turbine. So that is another challenge we have. So we need to understand how we can design a system where we can reduce NOx and CO emissions simultaneously. We can avoid blow off and flashback, and we will be in the stable region all the time without encountering combustion instability. So there are a lot of challenges when it comes to the hydrogen combustion. So in order to understand better about this, we just pay attention to this simple Bunsen burner you can see in a conical flame. So this conical structure you can see here, that's a flame cone. And you have a fresh gas velocity VU, and this red color is the flame front. The flame is trying to get into the burner, whereas the flow coming out of the burner is trying to keep the flame in that location. Mostly it is in conical shape. The off angle is the alpha here. So this SL is the laminar flame speed, which is balanced out by this, fresh mixture velocity. And if you plot this for different equivalence ratios is nothing but air-fuel ratio stoichiometric, which I mentioned that 34 kilogram per kilogram of fuel, or 17 kilogram of air per kilogram of methane. That number is the air-fuel ratio of stoichiometric divided by what is the actual mass of air by actual mass of fuel. Okay, that is the equivalence ratio. So basically, if equivalence ratio is 1, that is called stoichiometric mixture. We are providing exact amount of air to convert the entire fuel into oxidizer. If equivalence ratio goes below 1, that is called fuel lean. We are supplying more air than what is required to convert fully into products. And the other one is fuel rich. If we don't supply enough air, then we have more fuel than the air available to convert that reactant into products. So we end up with a lot of unburned reactants in the exhaust side. Now, if we pay attention to this number, this is a laminar burning velocity, the SL that I mentioned here in this graph. This is how the number changes. So you can see that the value is not linear, it is a non-linear shape. It has one kind of behavior below 1.1, another kind of behavior above 1.1. Okay, so it reaches peak around some point, and then it will start to taper down in both sides. And if you see different curves, the bottommost is the pure methane curve. On the topmost is the 40% of methane is replaced by hydrogen by volume. And as I mentioned before, hydrogen is highly reactive. The moment you start to replace methane or natural gas here by hydrogen, your reactivity start to pick up and your flame speed start to go up. So for example, in this, if I keep on changing my blend in this conical Bunsen burner without changing the fresh gas velocity, my flame speed is picking up. So what you can see is that the flames start to get into the burner. Okay, that is a flashback as I shown in the previous video. So that is why we have to pay attention to what equivalence ratio we are running, what kind of blending we are doing. So that is going to tell us what kind of flame speed we are dealing here. Okay. Then we have to think about the geometry of the system, and we have to make sure that our fresh gas velocity is always much higher than this lambda. So that is what I am going to show in terms of these different hydrogen blended burners. So you can see that a lot of options are there. These are all the different things. When we start to design a burner, we have to pay attention to these things. Our aim is to have low NOx, low CO and CO2 combustion. We need to have a turn-down ratio. What is a turn-down ratio means? Suppose you are designing a burner which has to run 1 to 10 means 1 kilowatt to 10 kilowatt. Okay, that is a turn-down ratio, 1:10. And the dynamics in the sense how the flame shape looks like, what is the size of the flame, and the combustion instability dynamics that comes into picture. And we aim to see the technological readiness level above 4. Then only the product will move from laboratory scale to industrial scale or laboratory scale to application side where customer can start to enjoy the product. And the other one is that we need to have a flexible fueling option. So the burner should have the capability to run with natural gas, LPG, syngas, ammonia, that kind of stuff. So, sorry? Okay, so what are the research that we have been doing at IIT Hyderabad to address these things? One is that we look into the domestic applications, community cooking applications that like canteen burners that you see in most of the tea shops and stalls. And then getting into the turbine premixed burner, stratified burner, multi-tube burner, as well as normal elliptical burner. So based on the time, I will show you a few of the examples. So we will just get into the laminar case first. So here the flow is laminar. So this is a typical domestic gas stove we are using in our home. Okay, LPG gas stove, that is a picture you can immediately recognize. So it has a mixing tube. LPG is injected through a nozzle, and the venturi, the mixing tube is nothing but a venturi. Because of the high velocity of the fuel jet getting into this, air will be entrained through the side holes. So in the mixing tube, we are doing a partial premixing of LPG with air, and that gets into the mixing tube, and you have a burner cap on top. That's where you realize the flame above it. The traditional things are like this flower pot kind of arrangement where you have circular ports. These things cannot handle higher percentage of hydrogen. So we thought of designing a new one. Instead of circular hole, we went with the elliptical hole aligned at a 45° to the flames of this burner cap surface. So this is a newly printed design from our lab, and this is how the flame will look like. Okay, when you burn, the flame has a swell component. So basically, swell means flow is rotating around itself. Okay, you can see it is clockwise rotating. And also you can see some kind of a yellowish color trapped within the bluish flame. This is slightly running at a higher partially premixing things. That means that it is fuel rich. We don't have enough oxygen to completely convert it into product. That is why you see some yellow color diffusion flame within inside, but it's mostly combusted later in a diffusion mode. So only very, very few smoke comes out of it. And this is the setup to do the actual research with that burner. So you see the stand here. This is the burner. say, sitting on a jack, so the height will be adjusted. And this is the vessel, and this is the burner, and you can see the loading height. Loading height is nothing but the distance between the burner head and the vessel bottom. So we are using some, master controllers, LPG, hydrogen. So we know how much amount of fuel we are injecting in it. So hydrogen and LPG are mixed together and then injected through the traditional nozzle what we have in our domestic gas stove. No changes there. We haven't done any other changes other than this newly printed burner cap on top of it. Okay, that is the idea here. And we use this one I am showing is the direct image. Basically, you take any camera, our own mobile, how the mobile sees the flame, that is what shown here. But to know what is going on, actually, we used a special camera called intensified CCD camera. So basically, it will, it's like a night vision camera. So we can see the wavelength in a very, very short bandwidth. So here we are looking into 310 plus or minus 5 nanometer. So basically, it collects the information which is OH radical. See, when we burn hydrogen, H2 with O2, it creates H plus O, OH comes out of it. Okay, so that says where the actual burning is happening. So that's why this direct image will look like when you see through this camera. So you can see that the hot spots, the reddish color, that's where the actual burning is taking place. All other things are plume, the hot plume coming out of the flame. And then what we do is, this is a line of sight image. So we do the ATAL inversion so that it is like if I slice the flame, at the middle of the flame, how the flame will look like. So that it will give me the flame front. Okay, this is how the flame front look like. So how the burner is, how the flame is burning above the burner cap and how it is bending. Okay, so that will give me an idea. So I am showing this for 3 different hydrogen blending. Here thermal input is 1.6 kilowatt in this burner. This is the burner cap, and you can see above how the flame looks like. So you can see that there are 3 different slots in that burner, 3 different rows, and we can see combined flame here. And the shape looks like the first one, H2 equal to 0% is nothing but pure LPG. Then we replace 34% of LPG by hydrogen by volume. The flame becomes shorter. Why? Hydrogen is much more reactive than the LPG, so your flame starts to move towards the burner. Okay, and if I go 50%, you can see that the flame is way too thin and it is very close to the burner cap. And if I put a vessel, so basically a pot above the flame, now you are compressing the flame by a vessel. The flame cannot go straight, it will start to go around the burner, around the vessel. So what you can see is that if it is a pure LPG, as I mentioned before, as we have seen in the previous video, this burner is creating soot formation. Okay, you can see the yellowish color. And when we replace the LPG by 35% hydrogen, you can see that hydrogen's high reactivity helps us to kill that smoke. Okay, the combustion becomes cleaner, and higher percentages, you can start to see the flame is getting very close to the burner. And getting too much closer to the burner is not good, because now instead of heating the vessel, we start to heat the burner. And if it is too much heat to the burner, then the flame can get into the system. That is the flashback, as I shown in the previous videos. That is not good. So then we tried different efficiencies, and what we can see is that we can achieve with this 3 new burner higher efficiency than the commercially available one. I don't want to bore you too much from here, but it shows the capability that this burner is working fine up to 50% volume, beyond which we have the issue with the flashback. So we have to rework on the design to go for higher blending percentages. Now getting into the canteen burner, which you can see in traditional tea stalls, this is some one type which is called the M22 burner. So the flame will come out, along the cylinder of the port. Okay, you can see the holes here. That's how the flame comes out. Here are the direct images. So you can see the 0% is pure LPG flame, how the flame will look like. You can see the different colors. Mostly it runs in a fuel rich side, equivalence ratio is above 1. That is why you can see the cyan color here. And when the moment we start to replace LPG by hydrogen, you can immediately observe the color changes. The cyan color disappears, becomes bluish color. Why? Because now hydrogen is much more reactive. So the equivalence ratio changes and the combustion behavior changes. So as we go higher and higher, the flame gets smaller and smaller. That you can see much better with the ICCT camera I have shown you before. So this is the OH intensity. So as you can see, when we replace with the LPG by hydrogen, initially the flame intensity is going up. So you can see much more brighter section, reddish color in this point. But at later point, what you can see is that the hydrogen is very reactive. It starts to try to penetrate into the burn. Okay, so it keep on getting smaller, compact, and closer to the burn. So what happens after 82%? We have something called flashback. Instead of flame burning here, the flame went to the bottom. Okay, it becomes a diffusion flame. Here is where the injection is happening and mixing with air. So instead of burning above, we ended up with a flashback below. Okay, that is not safe. So this burner the beauty is this burner is commercially available. Anybody can buy this, and we can immediately replace this with hydrogen. And you can see that it can handle easily 75% above hydrogen blending. Okay, which is the beauty of this. But we may have some efficiency drop because the flame configuration is different. Hydrocarbons have higher radiation structure compared to hydrogen. Hydrogen flame has a very low radiation heat transfer, mostly convection and conduction heat transfer. Okay, so we may pay some issues with the performance of this one. So I'll stop it at this point for laminar, and we will move into the turbulent case. Because in real applications, we can't go laminar, we have to go with the turbulent cases, because turbulence helps us to mix things faster, combustion will be fast, and your gas turbines, industrial boilers, industrial heaters, anything you take it, that will be highly turbulent in case. Okay, basically flow is turbulent, on top of it we are burning it. So the laminar flame speed that I mentioned before, here the flame speed will be easily 10 times of that or more than that based on the turbulence level we have. And one important turbulent burner is the swirl stabilized burner. This is very much used in most of the gas turbine applications. So the idea is very simple here. You have a solid region, core region in the middle, that is called bluff body. And then you have this blade kind of thing, like our fan kind of arrangement, we make it here. When flow gets into this, flow is going to rotate because of the stationary vanes we have here. Okay, so here it's a double swirl burner, and in the bottom one we have triple swirl burner. Basically, three different flow arrangements are there. You can see pilot, main, and tertiary. Here it's pilot and main. How the flame will look like, if you ignite a flame above it, you can see that the flame is looking like this. The flame is rotating because you are introducing a swirl component into this. Here the swirl is in counterclockwise direction. So when we ignite the flame is anchored on the shear layer and the tip of the burner. Okay, that is why you can see this kind of a conical strange shape. So this burner is printed using 3D printing technology, metal, stainless steel powder. And this burner is housed in this arrangement. So we have a diffuser and we have this 3D printed burner housed in this one. Fuel and oxidizer comes through this diffuser, enter into the burner, and above which we ignite the combustion, and the flame is studied inside this quartz plate arrangement. And as you can see, this is the actual structure of the thing. This is the diffuser section, and this is the where burner is sitting. These arrangements for the quartz plate to insert into this. So if you see the top view, you can see how the burner looks like. Okay, this is how 3D printed burner looks like. And this is an experimental arrangement. So we use different mass flow controllers, hydrogen, LPG. Mass flow controllers regulate the flow rate. It goes through the mixing chamber. Both are mixed in molecular level. Then they are further mixed with air. So all are pre-mixed. Pre-mixed means fuel and oxidizer are pre-mixed in a fundamental molecular level, like a gasoline engine, petrol engine we see. It goes through this. We create a flame above the burner, and this is surrounded by quartz window. And then we have the digital camera to take direct images. And we have the same ICCD camera that I explained before to see how the OH image looks like. So that will give us an idea about the flame structure. We also collected temperature through thermocouples and then emissions through gas analyzer. This is how the real flame looks like. And this I am going to show you for different airflow rate with the initial system. So you can see based on the flow rate, the flame speed has to match the flow rate. Then its structure is defined by the dynamic flow rate arrangement. Okay, when we push too much, then the flame will start to go up. And then if it is too much velocity, then the flame will disappear. That is called blowout. If the flow speed is very low, the flame will come back, sit on the burner. And if flame speed is faster than the flow speed, then the flame will enter into the burner. That's the flashback, as I mentioned before. Okay, so that is what we are seeing here. In the worst scenario, where the flame speed is much higher than the flow speed, the flame will enter inside the burner, and then it will start to burn inside. And that's why you can see the red hardness. The flame is too high, flame is burning inside the burner here, and it started heating the burner. So that's why the burner becomes red hot. Okay, the temperature is above 800 degrees Celsius. So this is how that it went further inside, and we used some perforated sheets to make the flow uniform. And some flashback conditions, it went and it destroyed those regions. So then we identified what is a stable region where we don't have blow off or we don't have a flashback, and we studied only stable combustion regions. So that is what I plotted here. So in this axis you have equivalence ratio. In this axis you have different hydrogen percentage by energy moles, and this axis is showing the bulk velocity. Okay, coming out of this one. Both the burners are having same cross-sectional area outside. But if you see the flow through the cross-sectional area, the double swirl burner, which has a lower number of blockage, has more cross-sectional area than a triple swirl burner, which has more of this bluff body region. And that creates a difference in the bulk velocity. More cross-sectional area, less bulk velocity, vice versa. So double swirl burner has a higher flow through area. So that's why for the same operating conditions, that means same mass flow rate of air, fuel, and everything I use, the bulk velocity is lower in the double swirl burner compared to the triple swirl burner. Okay, that is what the difference you can see here. And here I am showing you the difference, how the two burners, the flame structure will look like. Equivalence ratio is 0.6. That means we are having more air than what is required. Okay, fuel lean condition. And the thermal input is 20 kilowatt. And this side of the stuff, what I am showing is the triple swirl burner shape, and that side is double swirl burner. How, if I put together two flames together, how they will look like. So you can see that there are difference in the flame structure. And here there is a quartz wall, so the flame is hitting here. It is not fully anchored to the burner surface. It is, you can see it is lifted in both cases. This is a pure LPG case, and this is with 10% hydrogen and 30% hydrogen. So the moment you introduce hydrogen, hydrogen is highly reactive. The flame speed is much higher than the LPG. So you see the flame start to anchor on the burner. So flame becomes smaller, compact, and it is anchoring on the flame. So it means it is much more stable. And when you keep going higher and higher percentages, as we have seen before in the domestic burner also, the flame gets smaller because the reactivity is much higher. And that's why you can see the intensity also goes up. Then you can see how the NOx emissions and the CO emissions, because that's a major target for us. CO emission is very easy to understand. Whenever we don't have complete combustion, when we have incomplete combustion, we will have more CO emissions. So when we go too lean, our flame speed is very low, our adiabatic flame temperature is very low, we end up with incomplete combustion. Whereas at higher equivalence ratios, we mostly reach complete combustion. So CO emissions are very high when we go very lean. But that very lean conditions are very important to control the NOx emissions. So you can see that NOx and CO are like a newly married couple, like one goes opposite to other. So that is what you can see here. The NOx goes down, whereas CO goes up. Where CO goes down, NOx goes up. NOx is going to go up when you are going higher and higher equivalence ratios, higher temperature, because higher amount of hydrogen energy, more the flame temperature, more the NOx emissions. See, the problem with the industry is any industry, boiler, gas turbine, or any kind of applications we want to approach, the Indian standard as well as international emission standard says you need to control both. Okay, it's not like let me compromise on NOx emissions or let me compromise on CO emissions. We need to control both, and that's the challenge you can see here. Having both together going down is impossible. And when we go to NOx emissions in the triple swirl burner, where the bulk velocity is much higher, the incomplete combustion is more, because before we combust, they will be thrown out of the burner's location. Okay, so that is why you can see the CO emission is picking up. Combustion efficiency is slightly lower than the double swirl burner, so CO emissions are more and NOx emissions are low. NOx emissions are always high when you have better combustion, higher combustion efficiency, more temperature, more NOx emissions. If we compromise combustion, then we will reduce the NOx emissions. So we have to compromise efficiency, and then we can get the NOx emissions lower. Okay. So the triple swirl burner, by compromising the efficiency, it helps us to reduce the NOx a little bit, but we have to be careful. The operating range is very low, because the moment we go leaner side, we end up with more CO emissions. So this was with respect to swirl stabilized, and I want to take your attention to multi-tube burner. This is another one which we worked along with the startup company SBES. So they designed this burner and we printed it in Europe. It's a very big burner actually. The diameter of the burner is around 85 mm and it has single holes of 6 mm. The 3D image is here, and the printed version is shown here. So, and you see this white section is a pilot stage. I will explain you now. Here, this is called a co-flow arrangement. Okay, so air and hydrogen goes parallelly one after another, and that comes out like that. Unlike the previous burner, here both are vertically injected out. Okay, both are vertically coming out as a jet. In the middle, you have hydrogen surrounded by oxygen, air. So in every tube, you will have at the middle hydrogen coming out, surrounded by air coming out. Okay, so they are not mixed within the burner. So they are going to take some time to get out. It's like a jet coming out. Then hydrogen will diffuse into air. So there is some mixing length comes in, and then they will be ready for combustion. So this mixing happening outside the burner helps us to not bring the flame all the way to burner. Okay, so this is more like not a diffusion flame, but not a premixed one. This is called partially premixed burner. Okay, so that is the strategy people all over the world is understanding now. Because premixing, we will end up with either flashback or blow off. Whereas in the partial premixing, we can simultaneously address different problems, bringing more efficiency, lowering down the emissions, and safety to the flashback system. So that is what you can see here. And here, what is pilot means? Pilot has a different flame, this mixing length compared to the main fuel. Okay, so we introduce at 2 different stages. This is how the entire setup will look like. The printer one is actually sits here in a horizontal rig. We used to have a preheater, because in real applications, in gas turbine applications, the air temperature is not ambient. They will be elevated temperatures like 400 degrees Celsius, 500 degrees Celsius. With the application of preheater, we can heat the incoming air to that temperature, and then it will be burned inside. And this is the combustor section where the actual flame is traveling. And this is how the exhaust is taken out. And this is the overall configuration. Within the wall, we have this rig and we have this exhaust. Outside, we have this blower, the fume hood, and to take the product out. This just for size comparison, I am showing this how the exhaust fume hood looks like. So this is how we are taking the data. So as you see, we are seeing through the exhaust thing all the way through this one, and the burner will look like this. Okay, this is the burner, and this protruded thing is the electrode. Okay, with the electrode we are igniting the mixture, and then we are burning it at this location. And this is a typical DAC system, data acquisition system used here. So we are monitoring temperature and pressure at different sections, before burner, through burner, and after burner, not to know when the flashback is going to occur and what kind of temperatures we are facing at different locations. So some of the temperatures are mentioned here. So this is how the view through exhaust port will look like. This is one typical image. The bluish color is the LPG, and the slight orange color is the hydrogen flame. And the pilot is where the LPG is given. That is why you can see that color is only through this inverted Y. All other regions we are having hydrogen. And this is a pure hydrogen. 100% hydrogen is what we are burning in this burner. As I mentioned before, this burner can handle pure LPG to pure hydrogen. Why? Because the mixing is happening outside the burner. So the flashback cannot go back into the burner. There is an inherent safety of flashback inhibition. So you can see the different color. We are slightly rich in the pilot, leaner outside. So that is why you can see the bright color along the inverted Y section, different color other than. Hydrogen combustion by definition is a transparent, colorless flame. In reality, you have water vapor. Water vapor is heated too much. So the water vapor start to give IR signal. Okay, the red color comes from water vapor. So this burner is capable of supporting different configurations. Basically, main and pilot, we can play with equivalence ratios. So based on the industry requirement. Okay, so we can have different configurations. Rich in main, lean in premixed, this pilot, or vice versa. And we can also make it leaner or richer. So you can see that the brightest is where equivalence ratio is 0.76, 0.76. This is a homogeneous mixture. There is no stratification. Whereas in other cases, you can see this one, we can hardly see the flame here because the temperature is too low. This is truly transparent combustion. The temperature is low, so we are not heated the water vapor to such a high temperature. So there is no signal coming out of this. And we also worked on a bigger sizes than that. The previous one, what I showed was 50 kilowatt. We also worked on a 200 kilowatt burner size. And because that capacity is much higher, we cannot have outside the system. The temperature is too high, so we kept it inside the box furnace. And the project is also supported by Facility for Low Carbon Technology Development, Deployment, FLCTD, under the UNIDO project. It's a United Nations sponsored project. We worked along with the industry partner here. So this is where the burner unit sits. This is how the flame will look like if you see from inside. This, again, this Y section in what shows the pilot flame where we are sending LPG. You can send LPG, natural gas, ammonia, whatever it is. And other places where you cannot see any color, you can see it's highly transparent. This is where the hydrogen is burning. Okay, so LPG creates you the typical blue color, whereas hydrogen is not showing any color. And this reddish color around it is basically the box furnace material itself. Okay, this high temperature thing applied around it, that is glowing because it is heated too much. It is losing its IR signal. So this is how it will look like if you open this side door. How the flame look like from inside, you can see here. So this is how the flame will look like. It's a very lengthy flame. Unlike a swirl stabilized burner, here the flame is more like a jet flame, more like a diffusion flame. It's very long, and some industry boilers needs a longer flame so that heat can be given to larger places. Heating would be easier. And the color, as I mentioned before, comes purely from water vapor and some inert impurities. Okay, it's not soot or anything. There is no soot in this one. This is pure hydrogen flame. Okay, I will show it again. So you can see how long the flame is, how hot is this combustion is. The one problem what we can expect here is that NOx emissions are going to be very high because we are running at very close to stoichiometric and we are running at a very high temperature. So NOx emissions are going to be very high. And here we are running this to show that it is flashback proof. We don't need to worry about flashback in this situation. That is why I'm showing this. But if you keep it leaner, then the temperature goes down and NOx emissions can be addressed. And this is a final burner in my talk. This is the one idea which we have been working on. This is like an extension of the multi-tube burner. In the multi-tube burner, the one problem we are facing is that the mixing length is not shorter. So in swirl stabilized burner, mixing length is very short, but we have a problem with the flashback. Whereas in multi-tube burner, we don't have a problem with the flashback, but we do have a problem with the flame length. In a real gas turbine applications, you need a shorter flame. You don't need a longer flame in a gas turbine applications. So one way is to see if we can address this through this kind of a burner. So here we are creating an elliptical cavity, okay, all around this burner. And we have inner hole also here, so that some interaction will happen. If you see, this is how the 3D printed burner will look like. This is a bottom view and this is a top view, and this hole is appearing here. This hole is communicated to all other elliptical holes through these side holes. So we are creating some kind of a venturi, some instability creates, so we can suck some exhaust back into this. As I shown the flame, you can understand better. And if you see how the fluid flow looks like, it's nothing but inverse of cavity. Okay, how the cavity, if you fill the material through the cavity, this is how it will look like. So you can see that the cavity is slowly spinning. So when the flow comes out, the flow will spin and come out. Okay, that way you can impose some swirling motion to the flow. And the swirling motion helps us to make the mixing shorter, hold the flame longer. Okay, so your combustion will be smaller. So this is a number we are using. 8 liters per minute is a LPG. 45 liters per minute is hydrogen flow rate. In terms of mass, hydrogen is 18%. In terms of volume, 85%. In terms of energy, is 37%. So this is another issue when you do hydrogen enrichment. They come with different numbers because hydrogen by mass has a very high energy, but by volume it has a very low energy. That is why we are replacing only 18% of fossil fuel by hydrogen, but the corresponding number by volume, it is 85% of hydrogen compared to LPG. Okay, that is a problem. So the burner geometry has to work differently. Again, we are using 20 kilowatt here. And what I am going to show you is that two different cases. One is a 400 mm quartz tube. So this yellow color is the burner printed here. And we are placing a quartz tube above it. Okay, it's a kind of a semi-confinement. In real applications, you always have a confinement. Basically, you don't have an open flame. We have to burn it inside some combustor. And we have to raise the pressure and temperature, which will be expanded in turbine section in the gas turbine applications. Or in boiler, it will be going through the heat exchanger applications. So here, what I'm going to show you is by changing the size of the quartz tube, basically you are changing the cavity length, we will end up with a very different behavior of the burner. Okay, we are not doing any other changes here. We are just putting two different quartz tube, either 200 mm or 400 mm, and you will see how the flame looks like. So this is how the flame structure will look like for a 400 mm quartz tube. This is a typical OH image, double inverted one. Basically, you have a flame, you take a knife and cut it at the middle. This is how the flame will look like. Okay, and the equivalence ratio is mentioned here. 0.51 is very lean, and we are slowly reducing the air, keeping the fuel flow rates constant. So by keep on reducing the air, you are keep on increasing the stoichiometric, this equivalence ratio. We are getting closer to the stoichiometric. Higher flame speed, higher combustion rate. So the flame becomes smaller and smaller. It starts to get closer and closer to the burner. So if you plot the curve, you can see that the flame height drops immediately at lower equivalence ratios, and after some time they become stable. This is, we start from 0.51 and we slowly keep on going to 0.76. Then from there, you go from 0.76 and keep on increasing the air again. What happens if I start to go from there to here? So when I started initially, the burner is cold. It has a different behavior. Now we are running this for half an hour and then we are going back. Now everything is hot, so your behavior changes. This is called a hysteresis effect. So in real applications, hydrogen flashback happens also due to the thermal boundary changes. Your thermal boundary is changing with respect to time. So your flame shape also changes. You can see huge difference at 0.51. This flame looks bigger, whereas this flame looks smaller. Why? Because now the temperature of the combustor is much higher, so it can support better combustion. Better combustion, shorter the flame length is. And if you see how the time series looks like, let's say that I watch the flame and I watch the intensity of the flame. Is the intensity is constant or is the intensity is going through changes? If intensity is going through the changes, that is called thermoacoustic instability that I showed in the introduction time. So when we go from very lean to lean, here I'm showing the equivalence ratios. 0.51, you see it's very random thing. It's like our ECG. Okay. 0.53, you start to see some sinusoidal curve and some randomness. So this is called intermittent approach. And at 0.56, you start to see some kind of sinusoidal wave. Okay, so something going up and down in a regular manner and keeps on going up 0.59, 0.63, 0.67. And suddenly when you go to 0.71, everything disappeared. This bigger sinusoidal wave is not there here. At 0.76 also same. Whenever you see sinusoidal curve like this, that is a thermoacoustic instability. And when we start to go from 0.76 to 0.51 back, your thermal conditions are different. You most of the time you won't see a difference, but at 0.53, the green location, the corresponding thing if you see, it is much more sinusoidal. That means now thermoacoustic instability is there, which was not there before. Okay, because our temperature boundary conditions are different. In order to understand better, I am showing you the video how the flame looks like. But for 0.51, it is very random. You don't see any typical shape. It's a typical anchored flame just moving around. Now I go to 0.67. Now I hope you can follow me. You can understand what is going on. You can see that it is the brightness is oscillating, sometimes bright, sometimes dull, and it is going through the sinusoidal curve. So this is called thermoacoustic instability. So what is happening here is your heat release rate is not a constant number. Let's say if it is 20 kilowatt, it is like oscillating now. Sometimes 15 kilowatt, 25 kilowatt, 10 kilowatt, like that. Your flame heat release rate is oscillating, which is not a good news, because if it is happens in the real gas turbine, your turbine section is going to face enormous amount of pressure fluctuations. Sometimes entire combustor will be, damaged. And miraculously, when we go to 0.71, you see everything disappeared. The flame intensity is a constant number. You don't see the bright and dull, oscillating. You see a slight variation, but not so high. This is the problem with the thermoacoustic instability. It is highly nonlinear in behavior. Okay. For a given burner, given operating conditions, given confinement, sometimes it will go through thermoacoustic instability, sometimes not. So every burner we have to do for the entire operating system, and we have to address and understand what is going on in order to do the mitigations, in order to see how to address this. Now I am showing what happens when I simply replace 400 mm tube by 200 mm tube. You can immediately see the shapes are very different. Okay, you can see this shape is like this, whereas this shape is much different. So we can see the flame structure is changed a lot. There is nothing we have done in the bottom side. Same burner, same combustor section. Only the length of the quartz tube is changed from 400 to 200. And you can see, so it shows how the boundary conditions has a say on flame structure. And this is a real problem in actual gas turbines. And if I compare the same thermoacoustic instability thing, 400 and 200, what you can see is that at some places where there is no instability at all at 400 mm, there is a strong instability at 200 mm. Okay, and where there is a strong instability in 200 mm, there is nothing in the 400 mm. That is how the behavior changes. It's all because of the complicated non-linear relationship between heat release rate, pressure fluctuation, and velocity fluctuations. So this is another nightmare we have. See, we want to reduce our NOx emissions. So for that, we want to go linear side. We want to go 0.6, 0.7. But when we go to there and we confine the system, we end up with thermoacoustic instabilities. And again, it is not a universal behavior. Every combustor, every burner, every operating conditions has a different thing. Here, for example, if I preheat the air or if I change the thermal input, the behavior would be completely different. So for every operating conditions, we need to understand this, and we have to see how we can address the problem. Okay. So with that, I will stop and I will just give you the summary. Then we will have a question and answer session. So what I hope I have convinced you is that hydrogen blending with LPG helps us to stabilize the flame. It expands the operating range. It eliminates soot, as we have seen in the domestic burner, and it extends the flammability limit. Basically, hydrogen highly reactive, so it would allow us to go linear side with the help of hydrogen. So partially premixed combustion especially offers a better operating strategy, so that it's much better than the premixed. It's much more safer. Okay, premixed flame encounters the flashback, whereas partially premixed flame would allow us to not encounter in a short range. The cooking burners, currently we can handle 50, and we are working on it. Our new design handled up to 75% hydrogen blend, and we are targeting now for 100%, where one burner can operate both the things. Okay, either I can burn LPG, PNG, piped natural gas, or hydrogen. Okay, that is the idea. We are working on it. The laboratory burners, which I have shown, the swirl stabilized and the elliptical burner, we have seen we can go all the way to 100% hydrogen by partially premixing. With a caveat, NOx and CO emissions, there will be some compromise. The industrial burners also can handle 100% hydrogen. I have shown you the multi-tubular burner, and it had handled 20% LPG blend by mass, because it cannot go to fully LPG side, because it is designed for hydrogen applications. With that, I would like to thank Professor Manish Kumar for giving this opportunity to interact with all of you. And we got a lot of help from our own internal team for 3D printing, industrial partners, my PhD student and lab technician, and all our single workshop staffs. So thank you once again. Open for questions now.
So thank you so much for your session on mostly devoted on the application of the hydrogen in commercial and domestic burners, and that it is a very new topic. So far, we have had the sessions for the past 5 days. It's really a enlightening session and enriching session for us. Hope our participants have enjoyed it. Now the forum is open to all. The participants can interact with our next speaker, Dr. Saravanan sir. You can unmute your mic and you can figure out your question. Otherwise, you can put your questions in the chat box.
Good evening, sir.
Good evening.
Very good session, sir. It is a really enjoyable session. Thank you for the student of ours, sir.
Thank you.
Already, sir, there is some noises from your side, sir.
Okay, sir.
Otherwise, you can type, sir.
Otherwise,
we can,
yeah,
we can
you
answer
can
to
put
your
in your,
question.
yes, sir.
Okay,
You
sir.
can put in the chat box, sir. Yes,
Okay, sir.
there are some noises.
Please type your questions and I will happy to answer it. Because one thing we love as faculty is the questions from audience. Okay, it's like clapping somebody to auditions. For us, questions are very important.
Good evening, sir.
Yeah,
Sir, good evening. I am Dr. Chandrasekharan, Professor Mechanical, SRM ISD, Katamottur.
Yes, sir. Okay.
Sir, sir has presented very well, a nice presentation. Sir, I have one question that you told that the same burner for multiple fuel.
Yes,
How the burner can able to accommodate multiple fuel for a given geometry, because every fuel has different burning characteristics, as well as heat of release also may be differ. How you are able to accommodate this in a single?
Yes, sir. Very good question. Very good question. In fact, that is the key challenge we are facing here, a fuel flexible burner. So one idea is we go for a partially premixing. So we don't want to fully premix anything. Then this laminar burning velocity is a fundamental one that will have a say. For a given
Yes.
geometry is always fixed. Once we fabricate, we cannot touch the geometry. So we have to play with the flow arrangement. So what we do is partially premixing. So it is premixed to lean level, then we do a later injection. It is very similar to the gasoline direct injection engines, the gasoline engines that we have. Petrol engines. So the petrol engine also uses this GDI approach.
Okay.
So this is called stratified combustion. So you don't fully premix everything. So we play with the chemistry.
But it depends upon the fuel you are going to mix. Do you have any control for it? How much to pre-mix like that? How
Yes,
much
sir.
has to
Yes,
mix?
sir. So basically, we will have multiple injection points. Some points we inject hydrogen, and some point we introduce hydrocarbons. So basically, most of the things, the strategy is something called micro mixing is the latest solution for hydrogen. We introduce hydrogen very close to the exit of the burner. So we don't give too much time for it to mix fully. So the amount of mixture available, the volume of mixture is very small. Even flashback happens, it won't kill the burner. So that is the idea. All the heavy industries like Siemens, GE, all are going into that direction now. It's called micro.
Have you experienced this knocking, something detonation happens during the operation?
Those things happens in the IC engines field, sir, where we are pressurizing it. But in the combustion, in this kind of things, the thermoacoustics is very similar to that. Very similar to knocking what we observe in the engine.
Okay, sir. Okay. Very good idea, sir. Very good idea. Appreciate.
Thank you
very much.
Thank you so much. Thank you. Will it burn when I use lean mixture without adding hydrocarbon gas to avoid CO? Lean mixture, the problem is avoiding CO is very difficult. As I mentioned, we will end up with incomplete combustion because flame temperature drops a lot when we go leaner and leaner side. So we can reduce NOx emissions, but we cannot fully reduce the CO emissions. So that's a problem. Second thing is that when we go lean side, thermoacoustic instability is always there. That is something we cannot avoid, that we learn. So it's a very, very narrow range what people have to use. Shall we use any type of fuels, blended fuels, biofuels too in this burner? Yes, syngas is one kind of thing where the calorific value will be very different based on the amount of H2CO ratio we have. Swirl stabilized burner always provides more operating range than a normal burner. But the problem is all of them have some kind of limitations. On one side, you have a blow off, flame extinguishes. The other side, flashback, flame gets into that. Like how the previous professor asked the question, it's very hard to expand the operating range where I have one burner where I can burn anything at any equivalence ratio. That is impossible. We still have to tune for particular industry application, particular range. Yeah, feedback link. Okay, that's something he will work out. When will hydrogen actually be mixed with LPG for? For domestic, currently what we are doing is that we are using the same configuration. So LPG is mixed with the hydrogen before it goes through the common tube. So in our regular domestic gas stove, if you see upside down, you can see a manifold and then goes to individual burners. So we are mixing way before. So hydrogen and LPG are fully mixed before it is going through the injector. But the problem is hydrogen, as I mentioned before, is a very, very light gas. The density is very light compared to LPG. LPG is heavier than air. Hydrogen is very, very lighter than air. So beyond certain limit, we cannot use the same nozzle because we start to choke the nozzle. That is a problem we are facing.
Sir, however, the challenges are there in the production of the hydrogen as well as the storage and transportation.
Yes, sir. Yes, sir. That's another big story. Production, we still not sure, and the storage and handling is another nightmare. So one idea is we want to go into ammonia instead of hydrogen. You produce hydrogen and convert into ammonia. Ammonia is very close to the LPG cylinder, what we are buying in our domestic applications. Same way we can store ammonia also. And ammonia is much more safer. It won't detonate. Burning is, but the combustion is again a very difficult story there. We don't have any carbon in ammonia, but we will have a lot of NOx emissions and N2O emissions. So those are also bigger greenhouse gas emissions. So Japanese are the pioneers. They are working a lot in this area where hydrogen handling is difficult, ammonia handling is easy because a lot of fertilizers and many industries are using ammonia already. So there is a existing infrastructure, handling, regulatory, all the things are there. Only problem is ammonia is not good for health, so we should not expose ourselves. And the flame speed is very low compared to hydrogen. So otherwise, hydrogen and ammonia are going to be the future fuels. Okay, that's the only we cannot keep on going with hydrocarbons, LPG or PNG or ethanol, methanol. That's a difficult story.
Sir, actually, ammonia cannot be installed in engine directly. We have to
Yes.
And
It
also
has
it
a
is,
very large vaporization, so charge cooling is too much.
and one
Burning
more
itself is a challenge.
engines are corroded, sir.
Yeah, engine will corrode. So there will be a special chemical deposition that we have to do it for piston in walls and wherever ammonia touches, we have to take care of that. But the Japanese are already running in IC engines. Okay, they are already publishing a lot of paper. In fact, in our IIT Hyderabad also, we have one team started working on ammonia engine. So we are working on a dual fuel concept. So we will inject ammonia inside the engine. We start with the diesel, pick up the temperature, then we use ammonia, blend it with the diesel first, and then fully go into the ammonia. But
The ammonia,
again, challenges are there.
ammonia is higher hot ignition temperature, sir. That's why I'm asking, sir.
But it has a large charge cooling effect, sir. It's actually the other way around. You take ammonia in liquid form, we are injecting like diesel. And when it goes to vapor form, it has to take heat for that one, right? That is a charge cooling effect.
Yes, sir.
The
Because
ammonia is actually cooling down a lot more than the diesel. So
Yes.
we were unable to ignite it properly. That's what the simulation says us.
then breakthrough relations will down. Performance may affect it.
Yes, sir. So what we can do is we can go for higher compression ratio. In
Yes,
that
sir.
way, we can address it. But the problem is then how do we start the engine? Because when then the diesel, then there is a problem. So
Yes, sir.
both hydrogen and ammonia is not a straightforward answer. That is why we are coming in, right? We have challenges. We as engineer, we have to work on it.
Yes, sir.
There's a
With the
huge
people
potential in these areas.
dissociation, especially to how hydrogen will be split up and combustion will take parts.
Yes.
Okay, sir. Thank you, sir.
Thank you, sir. So whenever you have time, you can, you are all welcome. You can come anytime to our IIT Hyderabad. I'll be happy to show you the setup and, and any future collaboration also, if you want, I can help you out. Okay, I am open to that. It's important for us to connect with all the people, and you are always welcome.
Thank you, sir. Thank you. Any other questions from the participant sides? Otherwise, we can wind up the session if there is no other question from the participants. So actually, next session will be going with Dr. Vedaraj from NIT Trichy, sir. He's also going to present about this ammonia. And
Yes, I saw that. Very close to that. That's an interesting one.
Yes, sir.
Thank you, sir. Thank you all. Thank you all for the support. Okay, sir.
Thank you, sir. Thank you so much for kindly accepting our invitation immediately, and
it's my pleasure. Thank you so much,
sir.
Thank you, sir.
On behalf of the Department of Mechanical Engineering, Adishankara Deemed University, and on behalf of the participants who are all here, I thank you once again for spending your valuable time and giving a enlightening session on hydrogen and the other kind of stuff. Thank you so much, sir.
Thank you all. Thank you all. Bye-bye.
Thank you, sir.